include that, but 3-turn cycle and 8 leaves that it takes. So this is just a few examples of leaves following this pattern. Now I'm going to say this again, but I just want to go ahead and get it out there. Not every tree follows this pattern, and that's okay. It's following a pattern that we recognize, and it's not just the number of turns, it's the number of turns and the number of leaves. It's more than just a happy coincidence, I think, that these numbers are related together. Petals on flowers. Please don't ask me to name all these, because I don't know them. But we've got one leaf here. 2, 3, 5, 8, 13, 21, 34. I do have some examples of these. Let's look at the 3-petal lily. There are many types of lilies, but this one's got your 3 here. A 5-petal example, the California rose. The clematis has 8 petals. You can count these later if you want. 13 on the ragwort. And the aster has 21. And then the plantain. Couldn't get a good picture of that one, but yeah, you could see that there's plenty there stacked all together on one flower of plantain. Has 34 petals. And then some of these, like the sunflower, this family that I'm not going to pronounce in Latin, is 55 or up to 89 petals. And so these all follow this Fibonacci pattern where I can find one of these that's in my Fibonacci sequence. All right, the honeybees. Let's talk about honeybees a little bit. You have a queen, you have worker bees, and you have the bees with the wings that go about doing the commands of the queen. You have the drones and you have the worker bees. The worker bees are all, does anybody know? Worker bees are always what gender? What sex? They're all female, okay? And the drones are male, and one queen who has been given what they call the royal nectar. She's the only one that can produce eggs that can be fertilized. And so if she produces eggs that are not fertilized, they produce the female worker bees. And if they are fertilized, then they produce the male drones, which are able to help the queen reproduce and repopulate the colony. And then when they get big enough, they'll feed this royal nectar to one of the eggs that's been fertilized, and she will take a group with her to go start a new colony. Well, this looks like this with the family tree. You start down here with the male, and the queen bee, she fertilizes an egg and produces a male and a queen. This male will mate with the queen, and they will produce another queen that will have to mate with a male who reproduce. But meanwhile, this male reproduces with another queen that produces a queen that produces a queen. There's another shape here that we'll get to at the end. I'll either jump back to the slide or just remind you of it. This is a fractal. You guys know about fractals, and if not, you will by the end of the seminar. Fractal shapes will have these repeating patterns, but you've got these triangles that are built up of triangles. And so let's count how many. We're actually going to start with the drone. We've got 1 in this generation who mates with the queen, 1 in that generation, to provide 2 in the next sequence. Provides 3. Let's get them all up there. 3, 5, 8, 13, so on and so forth. And this is how the honeybee population reproduces in mass. So it's kind of cool to see these numbers. But you can pick any sequence, really, and say, well, I see these numbers everywhere. I like even numbers. So I noticed that all insects have even numbers of legs. Or cephalopods have even numbers of legs. Or birds have even numbers of legs. It's not just the coincidence of even numbers. I like even numbers. I like this pattern of 1, 2, 3, 5, 8, 13. There's relationships that these don't occur in other sequences, that this is the pattern for the male honeybee. So here's my disclaimer then. Not every flower or tree qualifies for this. You will find some. Ooh, I found a 6-petal flower. Maybe somebody pulled one off? Pulled a couple of them off? Maybe that's just a flower that doesn't follow the Fibonacci series. That's fine. I am not saying tonight that the Fibonacci sequence explains all math in all of nature. Please don't hear that. Please don't leave this room saying that. I'm going to share with you some resources that really debunk anybody that says that, and that's not my claim. But what I am saying is that these numbers do show up in nature, and it's more than just pick a number and we'll find it. I could find 15 somewhere in nature There's a relationship between these. Obviously with the honeybees, with the flowers, we're going to see it in a couple other instances as well. Like I said, this can be forced. Two numbers, a golden ratio does not make. I haven't even mentioned the golden ratio yet, but when you divide one Fibonacci number by the previous one, it leads to a value that we're going to look at in 2 slides. In 2 slides, I'll show you. But you can't just take any two numbers and say, oh, well, there you go, Fibonacci series. There's going to be a lot of things that it looks like the Fibonacci sequence applies, and it's just two numbers. It's just two numbers that are related. So be careful with that. And it works with other sequences. So you could have a geometric sequence. We're going to see that later on. Logarithmic series, those work also. So it's not just the Fibonacci series, but it's the one with the most popularity. And if you learn about these, you're going to get a lot of information about Fibonacci series. Here's the last thing, guys. There's this relationship. Euclid, the Greek geometry guy. Yeah, the Greek mathematician who knew a lot about geometry. And they gave us Euclidean geometry, which says that in a triangle on a flat surface, you have a total of 180 degrees. And then what if you put that on a globe? That's actually not true. You have non-Euclidean geometry when you have a triangle on a globe or in a curve. That same guy, Euclid, he actually understood this relationship of the golden mean or the golden ratio or the big numbers to the small numbers. And so some people will try to give you these relationships with, the dorsal fin on a dolphin is related to the length of the whole dolphin by these Fibonacci numbers. And that may be true, depending on where you measure. You can actually force these numbers to work anywhere. I've seen a lot of information about the golden numbers working with architecture, or the beauty of the human face, or many other things, okay? Where are you measuring from? Because if I measure from the outside of my eye, inside of my eyelid, if I'm measuring from the tip of my nose, or to the hairs at the tip of my nose, I can really force those numbers to look like anything I want. So let's not fudge the numbers. Let's not force the equation to fit where it doesn't. If it's there, let's accept it. But you have all these came from the same website where they were trying to make these points, and maybe some of them are legitimate, but is every fish going to have the same length tail fins? Probably not. They're just like people. They're just like fingerprints. They're just like snowflakes. And so we don't want to see it in places that it's not. You've got to be careful with that. But where it fits, don't ignore it. It's there. It's there. All right. We are going to do a math trick, but I need somebody who's got a calculator handy. Got a smartphone? That'll work. Anybody with a smartphone? Yes, okay. So what I'd like somebody to do, and I'm going to do this on paper so you guys know I'm not punching in my calculator. I'd like somebody to pick any two of the first, just because my multiplication by 11 is going to be kind of hard. Any two numbers from 89 down that are back to back. Just pick two of them. Shout them out.
21 and 34.
21 and 34. So if you'll take 21 and 34, and then count from 20. I want the next 10 numbers from there. So let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So add all 10 of those and hold your answer. 1, 2. 41, 47?
Okay, I'm still typing.
Oh, okay.
Of course, you have a trick up your sleeve.
I do. That's why I said math trick on the screen.
41, 47.
Oh, hey, how about that? Isn't that what I wrote? 41, 47? And what did I write on this piece of paper?
1597 divided by 21. 377 times 20.
I wrote 377, and then the answer.
Oh.
So I'm going to show you how this trick works. That was actually pretty good. I was faster than I thought I'd be. So how does this trick work? You these are Fibonacci series. Okay, so 10 numbers in a row. If X is your first number, Y is your next number, and then of course you add those two to get the next number, and then you add this to these two to get your next number, and add this to this to get this number. And so this is just the algebraic way of saying you don't have to understand that to know how the trick works. I'm going to do it with any 10 terms in a row. It doesn't matter. We started with 21 and 34. 21 was our first number. 34 was our next number. If you add all these together and do a little bit of algebra, you're going to get this. 55x plus 88y. That's factorable by 11. So you pull out 11. 11 times, look at this, the 7th number. I take the 7th number in your series, multiply by 11. It will be the same as the sum of all 10 of your numbers. So you guys can try that on your own. I'll tell you one more time how it works. It works with any two, but if you're not good with your 11s times tables, or you just don't want to write it all out, so we pick two numbers, maybe 610 and 377. So this is our first number. We pick the 7th number. 1, 2, 3, 4, 5, 6. I'll multiply that number by 7, and it will be this number plus the next 9 all added together. Multiplied by 11. Multiply the 7th number times 11. That's the sum of all 2 numbers. There's your trick. Sorry, no rabbit out of the hat. That's what I got there, guys. So that's a fun one. All right, let's move on to the golden ratio. This is probably what most of you are familiar with. If you know about the Fibonacci series, then there's a pattern as you put the numbers together, okay? So we'll take any number of our Fibonacci series, our Fibonacci sequence, and divide it by the previous one. So if you do 1 divided by 1, we know that. This is why we got to throw out 0. What happens when you divide by 0? Oh, shame on you guys. Math teacher in the back can tell me. No. I'm gonna need that shirt turned in.
Yeah.
Who could tell me why you're not allowed to divide by 0? One person? 2 people?
Come on. She's your daughter.
Yeah, she is.
And I organized the thing.
Yeah, her math teacher. This lady here knows? Can you tell us why I can? Or she's Googling it maybe.
No.
Oh, okay. Oh, okay.
The answer is infinity, that's all.
It's along those lines. If you go from a calculus standpoint, yes, it is infinity. Do you remember why?
It's sad because it's like Cookie Monster says. If you have,
Yes.
if you invite no friends and no one comes to your party, then it's just sad.
What's the answer, MJ?
Undefined.
Undefined, okay? So if you have an iPhone, ask Siri, what's 0 divided by 0? She'll give you some humorous responses. Here's how I explain it to my students who are just learning for the first time. If I have $0 and I want to split it between 5 people, each person gets nothing. That's easy. But if I have $5, and I split it between 0 people, how much money does each person get? And you can't say 0 because I just broke the game. I said you have $5 to split between nobody. How much does each body get? There are no bodies. There's no body there to give the money to. So the problem is nonsense. It does lead to infinity one way, positive infinity from the right, negative infinity from the left. It blows up your calculator. Try it. It'll give you an error message. So that's why we got to throw out 0. I warned you that was coming. But we'll do the next 2. So 1 divided by 1. What's the next Fibonacci number? 2 divided by 1 is? Easy. Come on, guys. 2. And then the next one is? This one's easy. 3 divided by 2 is 1.5. You didn't know this would be a math test today. 5 divided by 3, 1.6 repeating. 8 over 5, 1.6 termination. 1.625. That big thing there, and it keeps on going. Now we do have repeating patterns for these two, but I want you to notice this. 1 up to 2. Down to 1.5. Up to 1.666666, down to 1.6. Up to 1.625. Down to 1.615. Yep, that thing there, and then back up, and then back down, and what we get is kind of this picture right here. You get an oscillation. It's a damped oscillation. It's something we use in physics where we talk about like a swing. And if you just pull the kid back and you let go, it'll eventually die down. It's bouncing back and forth around this number. But this one would never end, of course. And so it approaches our magic number that we call phi. You might call it phi, 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 fo, fum. It's okay, guys. It's ancient Greek, so whatever you want to call it. But it's that symbol right there, and this is the number that we're approaching. Now I say approaches because it is an infinite series. I take the 1,000th term in the Fibonacci series and divide it by the 999th. Then it's going to be really close to this number, maybe up to 10 or 15 decimal places. But I have to go to infinity and beyond to figure out what exactly, but we can do with the tricks of calculus, we can figure out what the numbers are going to look like. So this is called the golden mean, the golden number, the divine proportion, the divine section, golden proportion. Leonardo da Vinci himself, he used this in some of his paintings. He called it the golden section. And so anything related around that, golden or divine, this is the number they're talking about. And it comes from the Fibonacci series. Now, a couple other fancy ways. I won't get too deep into the weeds here, but if you take the number and add 1 to it, it will equal itself squared. And that only works for this number. Or if you solve it algebraically and you get these two fancy things, you're going to see this in a moment. But it gives two answers, a positive and a negative. How can we get a negative answer? Do the Fibonacci series backwards. Count backwards with the Fibonacci series. Subtract to get, and you'll get that number right there. Notice these two, they're the same numbers, except for the 1 right there in the front. There's a lot of symmetry to these. That's what math does. It just makes sense, even when we don't know why. This one with a bunch of 5s in it, and I got one more. This one will make your head hurt. It's 1 plus 1 over phi gives us phi. Or phi. Which is 1 plus 1 over itself, 1 over itself, 1 over itself, 1 over itself. It goes on forever. It's a recursive formula, so it repeats itself over and over. I see that hand. Can you write down your question? Because we'll get into the end, okay? All right, so why do we care about this? There's a lot of math, and I want to see about nature. So I'm here, math and nature. Okay, well, let's get to that. But we need this rectangle, and then I'll show you the geometry and how it's related. You start with a rectangle, a square. It is a rectangle. Rectangles have 4 right angles, 1 by 1. We're going to split it in half, so we can find the bottom side here, and connect the midpoint of the bottom to the corner. You can do some trigonometry there, a little Pythagorean theorem, and you're going to get that the diagonal here is the square root of 5 over 2. Take that